Okay, so up first, so let's consider the equation 2 to the x equals 64, right? 2 to the x equals 64. That means you're asking yourself, what is x, right? What would x have to be to equal 64, correct? Or the equation log base 3x equals, log of 3x equals log of x minus 8, right? Again, you're asking yourself, what does x have to be for these two logs to be equal to each other, okay? What we're going to be doing is using one-to-one properties to evaluate them, okay? One-to-one property is saying that if for an exponential, if the bases are the same, all you have to do is set the exponents equal to each other, the powers equal to each other. One-to-one property for log is saying if it's the log of the same base, all you're doing is setting the arguments equal to each other, okay? So for example, if you look right here, it says 2 to the x minus 5 equals 64. Well, what we want to do is put 64 in terms of 2 to some power, okay? So you want to ask yourself, 2 to the what power is 64? And again, it makes me, I don't know why. As you can see, I really was circling. So we want to ask ourselves, 64, how can I put that in terms of 2? 2 to what power equals 64? Well, 2 to the 5th, right? So if you go through it really quick, 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 8. 2 to the 4 is 16. 16? No, you need 6. 8 squared. 8 times 2 is 16, right? It's not. It's 2 to the. Yeah, it would be 2 to the 6. And then 16 times 2 is 32. 32 times 6. 32 times 2 is 64. So it's 2 to the 6. Now that your bases are the same, all you're doing is setting your powers equal to each other. So you're asking yourself, x minus 5 equals 6. What is x? 11. You're so smart. Okay. Does that make sense? Okay. So when you do it for log, you have to make sure it's just the argument. So before I do anything here, I'm going to have to apply the exponent property or the power property, and I'm going to have to turn my coefficients into powers. Okay, so that means I have x to the 1/2 is going to be equal to 2 squared. Okay, so if I have x to the 1/2 equals to 2 squared, that means it equals 4, right? And how do I cancel out a half power? Negative. You square it. If I have a half power, I'm going to square it. What I do to one side, I do to the other. So this cancels out, and therefore x equals 16. Okay, so that's our goal when you are using the property. Yes. It would have to be something you can easily count out and not spend a lot of time trying to math your way through it. Hit refresh and it should be updated. All right, here we go. So example number 2. You wanted to teach it? Is that what you said? Oh, just checking. All right, so example number 2. We have 24 times 1/2 to the x third equals 6. Okay, so the first thing you need to do is to get our exponent by itself. So in order to isolate the exponent, that's our first goal, is to isolate. What do I need to do to isolate the exponent? How can I move that guy? Divide. I'm going to divide both sides by 24. So now I'm left with 1/2 x to the third equals, what does 6 over 24 reduce to? 1/4. Okay? Now your goal is to find a common base. So our goal is to find a common base. How can I make 1/2 and 1/4? I can't really change a half, but can I change a fourth? What could I do to a fourth? How could I rewrite? Anyone? What's 6 now? 1/2 to the 2. There we go. So we find a common base. So this one is going to stay a half to x third equals now 1/2 to the 2. And then now all you're going to do is solve your exponents. So you have x over 3 equals 2. So x has to be 6. The tricky part is going to be making them have the same base.
So whenever there's like two fractions of the same, you can automatically, like you don't have to, they just automatically cancel.
Yeah, so once your bases are the same, all you're left to do is worry about the power.
So they automatically move down, like there's nothing you can do to move down.
Yeah, you're just solving this. This is where the unknown is. Just worry about the power. Solve exponents. All right. Now for the next one. For a log, first thing you want to do is make sure to apply the power property. So step 1 is to apply your power property. Power property says that my coefficients can become powers. So we have log base 3 x squared equals log base 3 4 to the third. Are you good? Are you with me? And then step 2 is solve only the arguments. So you're going to set arguments equal to each other. Your arguments are what's inside of the log. Equal to each other and solve. And solve. It's just one big step. So here, my argument is x squared equals 4 to the third. So we have x squared equals 4 to the third is 64. So x has to be 8. Now, because I took the square root, technically x could also be -8, but it doesn't work in the problem. Okay? And that's because you can't have a negative argument. So this is what we call an extraneous solution. So this is our real solution. Because you can't, this x, when you take the square root, it produces a positive and a negative outcome, right? It's that plus or minus situation. But the negative can't be used because your argument can't be negative in the original. So if I plug that back into the original, it was like, uh-oh, error, error. All right. Okay. Any questions so far?
So
if an argument is negative, so if the argument, if your argument is negative.
So why did you make it, it's not negative? So why did you make it, why is it x equals -8?
Because when you take the square root of 64, it either can be a positive 8 or a negative 8. Positive 8 is our real solution. Negative 8 is our extraneous solution.
Extraneous?
Extraneous. So it's an extra that can't be applied. You would choose a root. It'll, maybe. I mean, it was said last year a little bit. All right. Next, we can use the definition of logs to rewrite exponential equations in order to solve. right? So being able to translate your log into an exponential is still pretty useful. So let's see what happens. So this is saying what? How can I write this as a exponential? Huh? Okay, 2 to what? There we go. 2 to the 5th equals 4x. It's your base result equals your argument. Base result equals the argument. So it's asking you 2 to the 5th equals 4x. 4 times x. 2 to the 5th is, what do we determine? Was it 32, right? 32 equals 4x. And then that gives us what? X equals 8. All right. Number 5 is an example of where we're going to use all of our properties because in order to solve, you want one log. Okay. So if I want one log value here, which property will allow me to combine? The product property, right? So the product property is what I'm going to use. So using product property, this becomes log of x times x plus 15 equals 2. Remember, when there is no base, it's common log. So your base is 10. So this is saying 10 to the second power equals x squared plus 15x. And then it becomes 100. When there isn't a base, it's called common log, which means your base is 10. And how do you solve a quadratic? You can use quadratic formula or factor. There we go. Minus the 100 and factor. What multiplies to give me a negative 100, but adds to give me 15? 5 and 20. What kind of 5 and 20? Negative 5 and a positive 20. Huh? What multiplies to give me negative 100, but adds to give me 15? So that means we get x equals positive 5 and x equals negative 20, which is my real. This is my real and this is my what? Extraneous. That's because I would have a negative 20 alone in a log. And is that allowed? No, your argument can't be negative. Yes? How do we feel so far? We would have finished today if we didn't have 15 minutes less of class, which is frustrating.
Something like this.
Okay, so we're going to continue. So what else did I do? Here we have example number 6. In example number 6, we're going to use log to help us solve an exponential. So we're going to convert our exponential into a log. So remember, when you're converting a log, it's still going to be the same base. So it's going to be log base 8. 8x minus 3. And I'm going to take the log of the other side because what I do to one side, I have to do to the other. So now I'm taking log base 8 on both sides. When you take property here, this is the identity property for logs. If you take the log of an exponential of the same base, they basically cancel each other out. So we're left with just x minus 3 equals log base 8 of 26. Okay. And then to get x by itself, I need to add 3. And what I do to one side, I'm going to do to the other. So that gives me x equals log base 8, 26 plus 3. Okay. If this is on the non-calculator side, this is what you would write. This is your exact value. Okay. And you would be done. Okay. If it was on a calculator side, that means they're expecting you to approximate. So you would plug that into the calculator as so. Log base 8, 26 plus 3. Remember, you can press math arrow up twice and you can put in the log base and it comes out to be 4 and 5, 5, 6, 6, 8. Okay. All right, here we're going to do an example where we're going to use natural log. So we're going to take the natural log of both sides in order to free our exponent over here. So when I take the natural log of e to the x, what I do to one side, I'm going to do to the other. Natural log of pi 1 plus x. Okay, so taking the natural log, now again, these are identity properties. They're going to basically cancel each other out. They're inverse properties. I'm sorry, they're inverses. So they're canceling each other out. So we're left with x equals, and I'm left with 1 plus x. I'm going to use the power property. And it becomes 1 plus x. Let's see. Thank you. Natural log of pi. Okay. And now I need to get all the x's to one side and all non-x's to the other side. So I'm going to distribute the natural log of pi. So I'm going to distribute. You get a natural log of pi. You get a natural log of pi. So we get x equals natural log of pi plus x natural log of pi. All terms with x are going to move to the other side. So when I move, I'm going to subtract x natural log of pi. So I'm left with x minus x natural log of pi equals natural log of pi. I don't know what I was writing there. Equals natural log of pi. Okay. I'm going to factor out the x. I'm going to factor out x. And when I factor out x, I'm left with 1 minus natural log of pi equals natural log of pi. So therefore, x equals the natural log of pi divided by 1 minus the natural log of pi. This again is my exact answer. So this would be, if I was on a non-calculator side, this would be your exact answer. If I had a calculator, then I would just put that in the calculator and approximate. And my approximate value would be -7 and 9. Something like that. Okay. So again, if you have a calculator, then more than likely you're going to approximate. Okay. If you don't have a calculator, more than likely they're just looking for the exact value. All right. The last part of this section is to talk about how to put this in the calculator. Now, if you have a calculator, it kind of makes things super duper easy. To solving by graphing, all you're doing is using your graphing section. You're going to put the left side in as your y1. You're going to put the right side in as your y2. And then you're just going to adjust your window. You have to be able to see the intersection, okay? So you have to see where, so this is key, adjusting your window, because you have to be able to see where they intersect. So after you do that, then you're going to press second. What do we press? I just had a brain part. Second. Well, you know what? Let me just look at it. Here's Sylvie. There she goes. Second trace. I don't know why that was not coming to my brain. So you're going to press second trace. Second. And then you're going to press trace. And then you're going to press intersection. So second, trace, intersect. And it's going to ask you, are you sure? Enter. Are you sure? Enter. Are you sure? Enter. Okay. So you're going to have to press enter literally 3 times. Okay. So I'm going to model that for you. I'm going to clear Sylvie. So we have second plus 7, 1, 2. And then I'm going to go to y equals. I'm going to put in my left side, which is 2 to the 3x. So 2 to the 3x is my y1. I'm going to put in my right side, which is going to be my y2, which is just 9. I'm going to go to graph. And notice how when I go to graph, I can't see where they intersect. So I'm going to go to window and I'm going to adjust my graph. I mean, I can't see, never mind. I was like, I can't, but I can. I can see where they intersect. If I couldn't, or if I want to zoom in more, I'm going to go to window and I can say, okay, I want to be able to zoom in a little more. So instead of going all the way to -10, let's go to -4. I know that x has to be less than 4. But we can make it 5, not 45. Count by 1. I know that my y minimum doesn't really matter because it's not going to go down there. So using some of your like knowledge of where things should be and how they should fall, you can go to 10 if you want. On the notes, this to go to 15. It's just more of a for the view of it. Sylvie, you know, she draws a little slow. So there's my exponential. And then here comes my constant, and I want to find their intersection. So I'm going to press second, trace, and then you see where it says intersect. I'm going to press 5. And it's like, is this your first curve? Yes. Is this your second curve? Yes. Do you really want to know? Yes. And you hit enter, and it tells you. So it tells you right here. Boom, there you go. This is where it intersects at 1 and some change. Not just some change, but so now I know x. So now I can say the value of x is approximately 1.0566. 1.0566. That's gonna be my approximate value. Okay. And that's it as far as with the calculator. And then over here, if you are doing it by table, you're basically trying to look and see where their values are close. So you would change your scale factor for your table setting. But I really would encourage the table setting because it just makes more sense to find the intersection, in my opinion. And that concludes this section.